This is Chapter 14, Lesson 1, and previously we've talked about the general ideas that affect rate, the general factors that affect the rate of a reaction. So here we're going to take a much closer look at how concentration affects the rate. And what we'll do is we will set up a bunch of different experiments, and in these experiments we will vary the initial concentrations of reactants and then measure the rate, the effect on the rate. And usually this is done using rate tables, like on the next slide. And analyzing these rate tables, we'll be able to determine how concentration, exactly how concentration affects our rate. So here's an example of a table. What we've got are general equations here. We have two reactants reacting together to form two products. Our rate table has 8 experiments. Each experiment has a different concentration of initial or reactants, or different initial concentrations for both reactants. In the case for the first experiment, for example, we have 0.0100 molar concentration of ammonium and 0.200 molar concentration of nitrite. And then we take a look at how this affects the rate. Now, in this case, and in all cases, almost all cases, we take a look at the initial rate. Remember that we said that the rate of a reaction decreases as it progresses, so we have to always check the same point throughout the reaction, and conveniently we decide to take a look at the beginning, the initial rate of the reaction. So if we take a look at this rate table, so we can say we've done 8 experiments and we have different rates that were produced. So comparing experiments 1 and 2, if we compare this experiment and the second experiment, what we see is that NO2 minus is held constant at 0.200, and the concentration of our first reactant, ammonium, is doubled. From here to here, we're multiplying by 2. And the reason we're keeping NO2 constant is because in this case we don't want NO2 to affect our rate. We simply want to see what ammonium does to the rate. And what we see is that in that time interval, or in this experiment, the rate doubles. So we go from 5 to about 10, 5.4 to 10.8. We also double in this case. So what we can say is that as you double the concentration of NH4+, the rate doubles. Now if we do the same thing and analyze a change in NO2, in this case take a look at experiment 5 and 6, what we see in this case, and notice by the way that NH4 in this case is held constant because we don't want NH4 to affect the rate as we're just studying this portion, and NO2 again doubles. We go from about 0.02 to about 0.04. In that same interval, you could see that the rate again doubles, times 2. So by studying how the change in concentration affects the rate, we can determine what kind of relationship that reactant has to the overall rate of the reaction. So as we summarize this, what we say in that first experiment, we saw that the concentration of NH4+ increases the rate by a proportional amount. So we can say that the rate is proportional. This is a proportionality symbol. It's not really mathematical. The equal sign is going to be the mathematical, and we'll need a constant before we put the equal sign in there. So this just means proportional. And in the second experiment, we determined the exact same thing for NO2 minus, nitrite. As we doubled NO2 minus, the rate doubled. So this is also directly proportional. So overall, we can say that the rate is directly proportional to both of these. Or if we want to make this into an equal sign, equal signs will require a constant to be introduced, because recall that constants simply relate your different variables. So if you're going to make an equation, you have to be able to relate these, and the constant will have units of both rate and concentration, as you'll see in this case. And this is famously called the rate law. We'll be able to write a bunch of these rate laws for different reactions. K is then called the rate constant. So we'll take a look at the next slide how to write one of these for another reaction. before we do that, we'd like to calculate the rate constant for the reaction above, and the way to do this is by simply taking a look at one of the experiments and taking numbers from one of our experiments. So why don't we come back just for a few, and why don't we go ahead and take a look at the very first experiment. We're going to use all these numbers to come up with our rate constant. So this will be our concentrations, and this will be our rate as we do this problem. So if we take a look, the rate law is written as rate equals a constant multiplied by the concentrations of our reactants, NH4 plus ammonium and NO2 minus nitrite. So because from the table we can get both the rate and the two concentrations, we can then solve for K. And to do that, essentially we'll just rearrange the equation. Let's go ahead and plug the numbers in so you can see where they came from, and then we'll rearrange to solve for K. For that very first reaction, our rate was 5.4 times 10 to the negative 7. And this was molarity per second, equals a constant. Our initial concentration of NH4 plus was 0.0100 molar, and essentially we're multiplying these together. NO2 minus was 0.200 molar. So rearranging the equation to solve for K, what we have is 5.4 times 10 to the negative 7 molarity per second divided by these two multiplied by one another, 0.0100 molar times 0.200 molar. And if we plug all these together, we should get an answer. So let's go ahead and work this out. .54 divided by and we should get ourselves a number that looks like this, 0.00027. This is our rate constant. Now, in addition to the number, we also want to keep the units. And in order to determine the units, what we'll have to do is cancel out anything that appears both on the bottom and on the top. In this case, molarity appears on top, which cancels out with one of the molarity that's on the bottom. What we're left with is seconds and molarity. Notice that both of these are actually on the bottom. Seconds is on the bottom of the numerator, which means overall it's on the bottom, and molarity is on the essentially on the denominator, which means it's on the bottom. So what we've got is this is per seconds and molarity. Seconds and molarity both go on the bottom. Another way of writing this is actually like so. To put seconds to the negative first and molarity to the negative first. In mathematics, negative first means it is on the bottom, on the denominator of the fraction. So this is your K, numerically as well as with the units. We'll say a few more things about rate laws, or really let's talk about what the rate law idea actually means. The rate law shows the relationship between the rate and the concentration of your reactants. So if you double a reactant, what does it do to the rate is the idea. The exponent on the reactants tells what's called the order of the reaction with respect to each reactant. So the reaction we just looked at, which recall was rate equals K times both our NH4 plus and our NO2 minus, and both of these had a 1 in the exponent. So we can say the reaction is first order with respect to NH4 plus. It's also first order with respect to NO2 minus. And all this really means is that if you double NH4 plus, the rate doubles. If you double NO2 minus, the rate doubles. That's kind of the idea. We can also talk about the overall rate of the reaction, and this is pretty simple. You simply add the individual orders, in this case First order from NH4, first order from NO2 together gives a second order. So this is a second order reaction, the one that we just looked at. So we can take a look at some rate laws, and here it says go ahead and determine the overall reaction order and the units for the constant, for K of each. We're not going to actually calculate K, we simply want to determine the units. So here's a reaction. What we see is there's a 1 in the exponent up here, which means this is a first order reaction. And since N2O5 is the only reactant expressed in the rate law, its order combines to give the overall order, which is order of 1. So you can say order equals 1 or first. This is first order reaction. In order to calculate K, the constant, what we'll have to do is rearrange the equation to solve for K. So in this case, K will be rate divided by the concentration of N2O5. So the units of rate is usually molarity per second, sometimes molarity per minute, but usually it's concentration per time. So in this case, we'll say it's molarity per second. The concentration of N2O5, brackets recall, designate molarity. So we have molarity on the bottom, and what happens is the molarities cancel out, and we are left with seconds. We are left with seconds on the bottom because it is, even though it's in the numerator, it's on the bottom of the numerator. So your units for K is seconds to the negative first. These are going to be the units for K. It's a first order reaction with these units for K, is the idea. Let's go ahead and take a look at the second one. Let me clear this. For the second one, what we see is we have our first reactant is second order. Our second reactant is first order. We usually don't write the 1. So overall, we have third order. This is a third order reaction. And let's go ahead and solve for K, for the units of K. If we had numbers, we can plug the numbers in. Because in this case we don't, we simply want the units. So let's rearrange the equation to solve for K. In this case, K will be rate divided by H2, concentration of H2 squared, times the concentration of I2 to the first power. So if we put the units in here, what we'll see is we have molarity per second for the rate. We have molarity squared for H2 times molarity for I2. So one of these molarities cancels out, and the other two molarities stay. So overall, what we have, let me write it down here, overall we have ourselves molarity squared, which is on the bottom, which means it'll be to the negative second, times seconds to the negative first. So these are going to be the units of K for the second equation here, for the second reaction rate law, we can say. Let's do the same thing for the last one then. This last one has a strange power. It's got to the 1/2. If you recall from mathematics, if anything to the 1/2 power, this means the square root of that something. So in a strange way, Cl2 in this reaction causes the rate to be affected in a square root fashion, and this is possible. These are a little more rare, but it's still possible. So by adding the two reactant orders, this is first order, we can say that overall the reaction is 1.5 order. Again, this is strange, and these are a little more rare, but you could still say it's 1.5 order. And then if you were to get the units of this, let's go ahead and do the same thing as we did on the other two. Let's rearrange to solve for K. In this case, K will equal rate over the concentration of CHCl3 times the concentration of Cl2. Again, rate is molarity per second. We have molarity on the bottom times molarity to the 1/2. And technically, again, these molarities cancel out. You're left with seconds and 1/2. Molarity to the 1/2. So our overall units will be molarity to the negative 1/2 times seconds to the negative 1. And this is going to be, this is going to be our overall reaction order. And you'll notice that in each case, the order will correspond to specific units, to unique units. And then really the exercise here is simply calculating the units of k, which units are extremely important in any sort of equation, and that's why we take the pains to do this. Finishing up, let's talk about a little more what this means, what these orders, individual orders, mean. It's possible for a reaction to be zero order, for a reactant to be a zero order in a specific reactant. And what this means is that the concentration of that reactant has no effect on the rate. So, for example, if you analyze this equation, if this reaction is to the 0th order, no matter how you change it, if you decide to double it, whatever new number you put in here for the concentration of CO, that to the 0th power gives you 1. And no matter if this is 1,000, to the 0th power still gives you 1. No matter how small, how big it gets, so you'll get 1, and it does not affect the rate. The rate does not change. In contrast, if it's first order reaction, if you were to double this, say if this goes from 2 up to 4, well, then likewise the rate must double as well. The rate must go times 2, and so forth. So we'll analyze this a little more in just a minute. But the first order reactant simply means that it affects the rate in exactly the same way as it is affected. So if you decide to cut, for example, the concentration of NO2 by half, well, if you divide it by 2, or cut it by half, the rate does likewise. It gets cut by half, is the idea. A second order reactant means that if you double the reactant, then the overall rate increases by a factor of times 2 to the second, which essentially, if you take a look at the rate law here, say we went, NO2 concentration was 2, so we made it from 2 to 4, so we effectively doubled the concentration. Well, this doubling then gets affected by the power, which means 2 to the second power gives you 4, so the rate then goes up by 4. And that's essentially how it works. If you were to triple it, as in this case, then you have to do tripled to the second power because, again, of this power, and you get times 9. So likewise, we can do a final example. So if you take, and if your NO concentration goes times 4, quadruples, the rate goes up times 16, because 4 to the second power is 16, and that essentially, this is literally how the rate will change if you adjust your concentration. And this is an important point. Here it says the rate law for any chemical reaction must be determined experimentally. We cannot predict it simply by looking at the chemical equation. Sometimes it matches, but it is not directly related to the balancing of the equation. In other words, the coefficients in front of a balanced equation don't necessarily relate to the order of the reaction. In this case, for example, you see that NO2 has a 1 in front. This is already balanced. CO has a 1, but in the case of CO, there's a 0 order. In the case of NO2, there's a second order. We'll analyze why this is so and how this is connected to the actual reaction mechanism in a future lesson. But for now, realize that this has to be done experimentally. You cannot just predict it from stoichiometry. Otherwise, there would be no reason to create these tables and do experiments. Otherwise, you'd be able to just go directly from the balanced equation, but you cannot. So why don't we finish up with an example of determining the actual rate law from given data. So our reaction has two reactants, A and B, and we took 3 different experiments and we varied the concentrations of both A and B and checked how the initial rate got affected. And then we're asked to write the rate law, determine the rate constant, or K, we'll have to get K, and then determine the rate for a third or for a fourth set of conditions when A and B are known to be this concentration. So let's first write the rate law, and then we can predict, using the rate law, then we can predict any concentrations that we put in. We can predict the rate that will result. That's kind of the idea. So on this next page I have the table reproduced, So remember that our rate law will always look like this. It'll always say rate equals your constant multiplied by your reactants. In this case, A, concentration of A times the concentration of B. And our task is to determine what kind of order A and B are based on the data table. Let's analyze the first two experiments. We see that in the first two experiments, the concentration of A is held constant. And we do that so we can see how the concentration of B gets affected, or how the concentration of B affects rate, rather. So we see that in experiment 1 and 2, we're doubling the concentration. So from here to here, we're going times 2. We're doubling the concentration of B. However, if you take a look, the rate does not change at all. The rate, you could say the rate goes up by 1 times 1, or does not change. So if we have no change, remember we said when the reactant concentration does not produce a change in the rate, this is called zero order. So what we'll have to do is put a 0 up here for B. Now if we take a similar look at the other set, so in this case, take a look now at reactants. Actually, we'll have to take a look at reactants, or experiment 1 and 3. And the reason we take a look at experiment 1 and 3 is that's when B is held constant. So that way B does not affect us in this case, but we take a look at A. So in the case of A here, we find that the concentration again doubles from 0.1 to 0.2. And then if we analyze the rate quadruples, goes up times 4. So anytime a doubling of the concentration produces a times 4 for the rate, we know that there's a second order. That reactant is second order. That's how, because 2 to the second power produces the 4. So we'll put a 2 in here for the concentration of A. So really our rate law, now anytime a reaction is 0 order, we usually exclude it, because if it's 0 order, this thing essentially becomes a 1 and we don't have to write it. So our rate law turns out to be rate equals K times A to the second power. And this is a second order reaction overall. So this is our portion A. Portion B asked us to calculate K. So we've done this previously. Let's quickly do it again. So rearrange the equation. K in this case is rate over the concentration of A squared. So in this case, the rate, what we'll do then is we can use any of our experiment. Let's go ahead and take a look at experiment 1. We'll use these values. So rate for experiment 1 is 4.0 times 10 to the negative 5th. And this is molarity per second. Let's go ahead and put molarity per second there. Divided by the concentration of A is 0.100 molar. And then we have to square this number. So when we square that, we get ourselves, if you plug all this in, we should get ourselves a fine value of, let's see, we should get ourselves 0.004 for the value. And for the units, because one of the molarities cancels out, one more molarity is left there, so we get ourselves a molarity to the negative first and second to the negative first for our constant. And then in part C, we are asked to calculate, say, a fourth experiment in which the concentrations are given to us. In this case, the concentrations are given as the the concentration of A is given to us as 0.050 molar, and B, concentration of B is given as 0.100. So what we can do now, molar, is just plug these values into the rate law that we've determined using the rate constant. So our rate will equal our rate constant, which is 0.004 molarity per second, multiplied by A, notice the rate law is A squared, multiplied by 0.050 molar squared. We don't have to include B because B was never, B dropped out, if you recall. So B really is 0th order, so will not affect the rate. So all we have is these two numbers. So go ahead and multiply them across and find out what you get. And you should get yourself a rate of 0.00001. And if you want to write this in scientific notation, this may be a little easier. We get ourselves 1 times 10 to the negative 5th. And then the units, because this is rate, the units should still be molarity per second. In fact, this molarity cancels out with one of these molarities. We're left with molarity per second. So it is molarity per second. More specifically, because we have two significant figures, we should really say 1.0 times 10 to the negative 5th molarity per second. And this is the final answer here. This would be the rate under these conditions. And this should conclude Lesson 1 of Chapter 14.